Hello everyone, my name is Henry Bright and this is going to be my simulation for Project 1, EAS3810. So we're going to be doing a 2D wind tunnel simulation and calibration. You can see all the specifics here, basically all the dimensions for the wind tunnel are given. We're going to be using ANSYS Fluent to simulate this. We're also given a formula for finding the test section velocity based on the fan frequency that would be operating the wind tunnel. So we're going to have three different cases, the 10 hertz, 30 hertz, and 50 hertz. But we're just going to do one of those cases for this video just to demonstrate it. And we're going to be using viscous turbulent flow. And then we're going to be getting contours for velocity, static pressure, total pressure, dynamic pressure, as well as some plots along the wind tunnel center line and the vertical test section center line. And then we'll also be doing that a plot of the pressure change in the contraction chamber versus the dynamic pressure in the test section. If we get a linear regression line relationship there, we'll be able to get the slope. That'll be our calibration constant. So I will kind of go through all of that now. So in this document here, I've kind of written out all the lengths. I converted to meters, just simpler for use in Fluent, just what I'm more used to. Gave us lines for those two, that center line and the vertical line in the center of the test section. Those will be helpful later on. And then just all the other heights. So let's go ahead and get started. The first thing I'm going to do is go ahead. We already opened up fluid flow and Fluent in the workbench on ANSYS. So I'm just going to go ahead and open up the geometry modeler. So I'm going with the design modeler. If you're familiar with Space Claim, you can use that too. This is just what I like to use, so that's what we're going to do. Our wind tunnel is going to be about 2 meters long, so I'm going to go ahead and zoom in to scale this appropriately so the dimensions are still not super funky. So we'll go ahead and do that. And then let's go ahead and get started with sketching. So there's a lot of different ways to do this. The main thing is I'm going to make the center of the test section the center at the origin, basically. That's going to be my plan. So I'm going to go ahead and do horizontal line here. We're going to constrain that with a midpoint constraint to the very center, so we make sure we get this at the center. For some reason that's not working. There we go. Okay. Then we'll do 2 lines to make the test section, 2 vertical lines to make the test section. And we'll constrain those basically the same way to the end of this line. Ends of this line. Okay, and then let's go ahead and dimension that. So both those will have our dimensions for that. Boom. Boom. And those are going to be the same dimension. The height of the test section is going to be 6 inches, but we convert that. It's going to be 0.1524 meters. So we're going to do the same height for both meters. And then we can go ahead and draw the horizontal lines connecting those. That'll be helpful. Because ultimately we need just the wall shape. We'll end up deleting these inner lines at the end. I'll get to that. But that's going to be, that'll come in at the end. So then we'll go ahead and have to dimension the length of the test section. The length of the test section is 12 inches. Convert that. That's going to be 0.3048 meters. Boom, we've got our test section. This is basically done there. So now let's start drawing some more. So I'm going to go ahead and do, I'm basically going to extend the center line to keep doing this. I'm going to go ahead and do the contraction chamber now. So just have a horizontal line extending from here, and then we'll have a vertical line there. Let's go ahead and constrain. Midpoint constraint to the end of this line. Awesome. And then let's do the height of that as well. Mention the height. And that's going to be the height of the entrance. Basically, the height of the entrance to the contraction chamber is going to be the height of our settling chamber, which is 15 inches. No, excuse me, 22 inches. So it's going to be 0.5588 meters. Excellent. That's what we like to see. And we'll go ahead and draw a line to connect those. So this is going to be angled because we're going to be contracting our flow. Makes sense. Boom. All right. And then we'll extend this line. Well, no, that's a lie. We won't extend this line. We'll just go ahead and draw the vertical or the horizontal lines coming out of here. Along with the vertical line connecting them, and we'll just constrain and dimension these here in a second. So constraints, we've got horizontal, boom, boom, although I think they already are. This one's vertical, awesome, and then we'll dimension this. So this length is, it's gonna be the length of our settling chamber, which is that one's that 15 inches that I mentioned earlier. So we're gonna have 0.381 meters. And then we'll dimension the height of this. No, that's a lie. We don't need to dimension the height of that because we've already done that. Because we have the horizontal and vertical constraints and it's constrained with that. So never mind. That is okay. We're good. So now the last thing is just to do the diffuser. So we'll do a similar process. Go ahead and draw out a line here. Awesome. And then we'll draw our vertical line for the exit of the diffuser. And go ahead and constrain that just like we've been doing. Midpoint constraint to the end of this line. Excellent. And then we'll connect these so that we have the rest of our wall essentially. Very careful to make sure you get the end point of these lines. Sometimes you can kind of like go over outside the edge to make sure that you get it right. Like, I don't think that's right. I don't know, it is. Okay. Should be okay. All right. So then we need to dimension a couple things. So we'll dimension the length here. Horizontal length. So between this point at the exit of the test section to the exit of the diffuser. We need that dimension for sure. And then we'll need, we should need a dimension. I don't know, it looks like it's trying to say that, this might say it's over constrained. No, we're okay. All right, then we'll need the height at the end of the diffuser. So H7, that's our length of the diffuser. That's our longest section. It's gonna be 42 inches, which is converts to 1.0668 meters. I'm looking off my other computer to see what I've written already. And then the height of the exit of the diffuser. This one we have to calculate. You use the half diffuser angle, which is 3 degrees. You basically do like the length of the diffuser times the tangent of 3 degrees, and then multiply that by 2 to give you, for both the upper and the lower, and then add in the height of the test section as well. So that ultimately comes up to 10.4 inches, and that converts to 0.2642 meters. And that looks beautiful. Okay, so now what we have to do is delete the inner lines so that we can generate this surface. So that's what I'm going to do. I'm not trying to delete an axis. And one more. Boom. Okay, that looks perfect. Awesome. So some of our dimensions and like maybe even constraints kind of go away, but it'll be okay because we're just going to go ahead and hit concept, search surface from sketches, and we need to select all of these. So I'm going to go ahead and hit control and then just click on all of the lines so that it incorporates all of them. Usually you can just like select the whole field, but for some reason that wasn't working for me today, so we're not going to worry about it. And so we'll hit apply, and then we just have to hit generate. And now we've got a solid looking surface. That's what we've been looking for this whole time. Awesome. So that looks good. If we go back over into our workbench, the geometry has been updated, it looks like. Let's just make sure. And it is. So we can go ahead and close our geometry and move on to the meshing. So I'm gonna go ahead and open that tab up. Might take a second here. So basically this step's a little tricky, can be a little time consuming just because sometimes depending on how finite of a mesh you're running, could take you a little while to run it. But pretty simple. We're basically gonna do just like an it's a pretty standard mesh using the triangles method. Once we get it opened up, I'll show you what that looks like, and we're just gonna adjust the element size a little bit to make it a little finer, just to give us the best possible results. It ends up running pretty well from my findings before, so should be pretty good. We'll wait for this to pull up with our sketch, and there it is. That's what we've been looking for. So yeah, so we've got our mesh here. You can see there. We want to go ahead and we'll just go ahead and generate that. Just give you an idea, yeah. So you can see it's very basic. We're gonna need to add a method, is what we're gonna do. So you right click on mesh and you have to insert, and then you want to do method. And it comes up with an automatic method. The geometry selection is just this. We need to hit that, hit apply. We'll go ahead and do this in 2D. This makes a little more sense. And then we're going to change this to triangles method. So that's good. And we're going to go back into our mesh settings. We're going to change the element size. It has a default. We're going to go ahead and do 5. It should be in millimeters. So 0.005 meters. That's what I've been using at least. And this will take maybe a second to generate. Not more than a second, a little bit longer. This is a decently finite mesh. So you'll see basically it should end up popping up as like almost black because it's just that finite. Yeah, that's exactly what you see. But when you zoom in, you can see how it's meshed with these triangles. So that's a good sign. That's what we like to see. So looks like our mesh is pretty good. The only thing we need to do left to do on this page is we're going to need to select a couple of our edges to form boundary, well, all of our edges to form boundary conditions. So we're going to basically name them. So if I like right click on this one and go ahead and do create named selection, that's what I'm looking for. We're going to have some different boundary conditions. So this one is going to be our velocity inlet. So that's one of the ones that we're going to be controlling. Very important. And then also this far right side, this one's going to be our pressure outlet. And then all the rest of them, I'm going to go ahead and hit control and select all the rest of the walls. And those are just going to be basically a stationary wall. Very simple. When we get into the simulation results, I'll be able to show you what that looks like. Tunnel wall and hit OK. And that should be good for what we're looking to do on the mesh. Our mesh should be good. It looks very good. So I'll go ahead and come back to the workbench and update that so we make sure it's got our mesh loaded in there. And now it does. So that's good. Go ahead and close our mesh page for now. And once we come back, we'll go ahead and do the setup. Take a second to open this up. Okay, so it opens up our little menu. Hopefully you can see this for the launcher. We're going to go ahead and hit double precision and increase the solver process to 2 just to help with computation. Hopefully should make things run a little smoother, ideally. And then you're just going to have a lot of boot up here with Fluent starting to pull up. So you'll probably see a lot of different screens here. But we'll just wait for it and then get started. And setting up our conditions here. We are almost set up. You can see our little wind tunnels popping up into the corner here. That's good news. Go ahead and hit OK and look at that. We are looking pretty good. All right, so let's get started with setting this up. You got like your general page here. Everything looks fine. Everything's pretty standard. Next thing we're gonna do, first thing you'll check is like your materials. So depending on what you're using, you might change this. In this case, we're just using air. And you can see it's got these properties already defined. Those are perfect for us. It's exactly what we want. Next thing we're going to check, we've got our cell zone conditions, and it's got the fluid that we want. So now we're going to do our boundary conditions. This is the next important step. So first is the inlet. It's already, you can see it's already defined it because we named those selections. So this is our velocity inlet, which is what it's looking at. So we have to adjust this. So this is important. This is where we use our test section velocity formula. So I already did these calculations. I'm not going to show them right now. But I'm going to do the 50 hertz case. Let me make this clear. I'm going to do the 50 hertz case for frequency. So when you calculate that, that gives us a test section velocity of 12.073 meters per second. And so we need to adjust the velocity inlet based on that. So we're given a contraction ratio initially. Problem is this is 2D, and with the turbulent effects of this flow, it's not going to give us a super accurate result. I ended up trying it initially, and it gave us a velocity, I think that was too low. Because the other issue is there's a given in the project, there's a given contraction ratio, but it doesn't match up with the height ratio as you would expect for the dimensions that were given. So I just went based on the dimensions that were given. So we had a slightly different ratio. Needless to say, so I used a first initial guess basically to try and get the test section velocity and just kind of checked where it was and then made adjustments, increased it, the inlet velocity if I needed it increased, decreased it if I needed it decreased. And so ultimately, like I used the area ratio or the height ratio that we actually used, which was 3.67 based on the dimensions given. And I tried that. That gave me a 3.29 meters per second velocity inlet. That didn't work. It was too low. So I ended up doing just a trial and error process testing this. And what I got was that 4.61 meters per second gave us pretty darn close. It was like 12.09, I think. We'll see what it ends up being. But we're gonna go ahead and hit that apply and go ahead and do that. That's gonna be our condition. The next thing is boundary conditions, the outlet, pressure outlet. You'll notice that this is measured in gauge pressure. So this is very important because we don't want to put our atmospheric pressure here. We want to put just gauge pressure. And at the exit, we want gauge pressure to be 0. It should be matching up at the exit with the pressure that we have outside the wind tunnel, which is atmospheric. So that is good. And then I mentioned earlier the wall. You can see the wind tunnel wall. That's our other boundary condition. It's going to just pop up as a stationary wall here. When we see it, yeah, stationary wall, no slip condition. We want that. That's important. I'll talk about that. So that's already applied, but we'll hit that and we're good to go there. Next thing is reference values. I checked this and I think it was interesting because our reference value we need to do for the, let's see. Pressure is 0 there. I'm not sure if that's supposed to be gauge pressure. It's really not clear. So I ended up adjusting it to atmospheric, which is 101,325 to try and get results relative to that. Because I know our exit condition is gauge pressure, but I wanted to try and get the results on the contours and plot or on the plots be just absolute pressure. It didn't end up working, and I don't think it will here, but that's what I did to try and get the best results, but that's okay. So yeah, everything should be defined and good now. So the next thing, all we have to do is we have to initialize this. It starts with 10 iterations. I usually do like 15 or 20 just to make sure that we get a low enough residuals. We'll go ahead and do the hybrid initialization, get everything ready. Take just a second. Yeah, I like those results. So we're good there. And now we get ready to run our calculation. So we're going to need to do iterations. I do about 150 just to try and get the best possible results. With this being viscous flow, it will probably need it. It probably won't even converge. It might, but hard to say. We'll see. Yeah, I think we're ready to go ahead and calculate. Here we go. So you'll see our residual plot kind of pop up, and you kind of follow along with that to see where it's headed. Everything's trending, well, mostly down right now, so that's what we like to see. Um, One thing I did do is I forgot to change. I don't know what type of. I did mess something up. I forgot to change the what's it called? Um, the type of flow. I don't know what type of flow this is actually. Um, calculations are complete, but let me check on that. I forgot. Yes, under models, that was one step I forgot. I'm so sorry. So it looks like we did have viscous flow, which is good. I was going to turn the energy equation on. And I'm probably going to just go ahead and run this again, just because I want to get the results similar to what I actually did on the project. K omega, that's fine. I think that's what no, I think I did K epsilon when I ran. Yes, I did K epsilon. So I'm gonna go ahead and just do exactly what I did on the project. There's several different types you see of turbulent flow, or equations for turbulent flow with these models. They're all gonna give you like maybe slightly different results. So let's scroll here. Okay, and I want enhanced wall treatment. Oh my goodness, it's gonna keep rescaling on me. This is so weird. Let's see, Mike. And then we want pressure and, oh my goodness, thermal effects on there as well. That should be good. That was just exactly what I did. Yeah, so we've changed this. Okay. That was one thing I forgot that was important. That's my mistake. So let's go ahead and reinitialize this. Yes, we don't want to save those calculations. Redo them. Okay, cool. And let's run that calculation again for 150 iterations. Because it'll probably take up, like I said, all of the iterations. You'll notice the other one converged, which is why I didn't end up doing the full number of iterations. Yeah, this looks much more like what I've been finding. So let's see what we end up getting. It'll take a little second here, but then I'll basically just show you how you can kind of, I'm not going to show you every single one, but basically just how you can get all the contours and plots and just show you what they look like to make sure they look the way they should. That's the plan. And then I'll kind of show you a little bit of what I did in Excel, how you can kind of write these to a file and take them into Excel and make the plots a little better because you can combine multiple cases. Like once you run the different frequency cases, you can combine those. And that makes things a lot better for comparing your results. So that'll definitely be worth looking into. You'll notice here you can see the plots have really stagnated. That's kind of to be expected with, like I said, doing the two equation method for simulating the turbulent flow. And we still have a pretty finite mesh, so I'm a little surprised, but that's what I've been getting. But it still gives you very accurate results, or what seem to be accurate results for general trends, at least, what we've been getting. So there we go. We're done there. So the first one we'll do is graphics, and that's where we have contours. So let's go ahead and do our contours. We'll start with the static pressure, and you'll want to do this for the interior surface body. We'll go ahead and compute and save and display. And if I exit out of here, you can see it. So looks pretty good. That's basically what we were looking for. So you can see static pressure greatest in the settling chamber. Once it contracts, velocity will go up, static pressure goes down. So you can see that and reflecting and going like the more like blue-green region, that's the lower static pressure. And then it increases through the diffuser. So that looks really good. I'll very briefly, I don't want to like explain all of these, but let's just very briefly go through all the rest of them. You can see dynamic pressure, basically opposite relationship. It's going to get a lot higher as the velocity increases. So that makes a lot of sense. That's what we like to see. And then total pressure is the other one that we were interested in. And this one makes perfect sense. Great explanation. constant basically throughout. That's the way it should be. The only issue is you'll see these boundary layers that develop. And it's super interesting because we've got turbulent flow. So we're of course going to have a boundary layer. It widens as the flow kind of develops. And that's where we see pressure loss because of viscous effects. So you can see that pressure's gone down. And that is very notable. Last one was velocity. I'll go ahead and compute and save and display that. Looks like something's wrong with the value here. It shouldn't be that high. Something might be a little off there because it should only be reaching a maximum of 12.073. So I might have put in the wrong inlet velocity perhaps. Something looks a little off, but I know when I did my simulation the first time, these were the results that I get. So I was just using those numbers. So if that's not the case, you can always just adjust these, and then they should be more accurate. So it could be different for everybody. But the main thing is we want to get a test section velocity, which is probably going to be about your maximum velocity. That should be equivalent to the one that we found from that formula using frequency. So that's a little off. I apologize for that, but it's okay. And then the last thing I'll show you is the plots. This is where we can get our plots. So for example, we can do static pressure on the interior surface body. No, this is important. Okay, so what we need to do is we were trying to find these plots along the center line of the wind tunnel. So you actually need to create a new surface. Not a point, sorry. Create a new surface, the line. You could call it horizontal. Just so you know, it's the horizontal center line. So of course, y is going to be 0 for both points. The actual dimensions, let's see, if you add up the lengths, it's going to be 2.3622 meters. So that means you just divide that by 2 and do the negative and then positive. So negative 1.1811 to 1.1811, and we'll hit create. Close that, and now we can measure it relative to the horizontal. Let's do static pressure. Beautiful. That's exactly the curve we're looking for. Where, like I said, again, you start high, it decreases through the contraction chamber, reaches its minimum, like kind of peters out through the test section, and then increases back up through the diffuser. So that's great to see. Dynamic pressure should be basically like the opposite of that. Yep, exactly what we would expect. And of course, total pressure. This looks weird, but if you look at the scale, it's all within, I don't know, 0.01, 0.001 pascals. So if you were to write this to a file, this is important. If you check write to a file, it'll write it to like a text file or like a .xy file. And you can actually open that with Excel, and it'll just give you 2 columns for like the X and Y component. And then you could plot it. And if you change the scale of it, you'll see it's just a horizontal line, which is exactly what we would expect. So that's good to see. And then of course, velocity, it's going to be basically like our dynamic pressure, because they're just related. It's incompressible, flow density is constant. So dynamic pressure is just variable based on velocity. So that's exactly the relationship we would look for. And then the only other thing to note is for doing the vertical line through the test section, you would have to change the plot direction so that it's x0, y1. That's like basically like your unit vector type of thing. And then you would have to create a new line. So you'd have to have, let's just say vertical, because we know where we're talking about in this case. So your x stays constant. It's going to be through 0. That's why we put our test section in the center. And then it's going to be half the height of the test section, which is negative 0.0762 meters to 0.0. Create that. Boom. Close that. And then if we get rid of our horizontal and our vertical, let's try velocity. Beautiful. And this looks very similar. Basically, this is what we would expect. You can see there's even the points going down to 0 velocity. That's because of that no slip condition by the wall. But then it's basically mostly developed and stays basically constant through the majority of that center line. That's exactly what we would expect to see. And you can see the same for pressure, all the different pressures. I'm not going to do that right now because I'm sure I'm going very long at this point. Yeah, I think that's a good summary of everything. The only other thing is that calibration. So what I did for the calibration is we need first the pressure change over the contraction chamber. So I ended up finding the lengths. I don't have them off the top of my head, but I ended up finding the lengths of like in X, in the X coordinates of where the contraction chamber started to where it ended. And I did a center line, a line through the center at y equals 0 to get the measurements of static pressure there so that I could then just write it to a file, get the maximum, get the minimum, subtract, and there I have that pressure change. That was very helpful. And then for finding the dynamic pressure, do basically the same thing, create another line that's horizontal through y equals 0 from beginning to the end of the test section. And then I actually just averaged those because it wasn't constant. Hypothetically, it probably should be, but being like a viscous turbulent flow, it's not going to be. So that was the easiest way I felt to do that. So I did that, and then I plotted. And let me pull up my Excel sheet with that plot. Here it is. So I ended up just summarizing them all here, the P in minus P out of the contraction chamber versus the dynamic pressure. This is the average, of course. And you get this nice little line, and it ended up being a perfect correlation with my data. R squared was equal to 1, so that's exactly what we wanted to see. But that slope, that 1.326, that's our calibration constant. And I suppose the last thing I meant to show you was just how you can like combine these plots. So like I said, this is kind of what your like .xy file would look like, because it would just have this column with all of the information from whatever you plotted. Your x coordinate, so x position, and in this case, velocity magnitude. And then I just ended up copying in the ones for like my 30 hertz case and for my 50, didn't type that here, 50 hertz case. And then I was able to just plot them all as like 3 separate series on this plot, so you can compare them. You can see like as frequency went up, velocity of course went up, but they followed the same pattern, at least when you scale the graph appropriately. So yeah, hopefully this helps you all. This is a good summary of how to complete this project and using Fluent for making a basic 2D incompressible low speed wind tunnel. So thank you for listening.